let us begin with our journey. We'll quickly start with neural networks and go through the basics. Then we will slowly delve deeper into the world of machine learning. So, what are neural networks? So, on my screen, I have the picture of a dog. So, when you look at this picture, the very moment you look at it, you know that it's a dog. But how? Like a usual program, you don't end up looking at the picture, then comparing it with other dogs that you have seen before today, and then making sure that yes, it is a dog, and then you don't say that it is a dog. As soon as you look at it, you just know that it is a dog. So with neural networks, this action of neurons, this functioning that happens as soon as you look at something, this is what you are trying to replicate with neural networks. So what are neural networks basically? These are just a series of algorithms that try to mimic the human brain, in which each neuron would represent a mathematical equation. Now that we are done with the definition, why do we really need neural networks? The main purpose that we use them for are prediction and classification. However, we can do that with other programs as well. For example, if I want to predict something, I can just have some input and then compare it with a large amount of data that I already have and just give out the closest value that I get. Or for classification, I can do the same. So why do we need neural networks? So whenever we are trying to predict something, for example, I have some data over here. I have a car, its mileage, capacity, power, and I want to predict its price. So I can just go through the data in the market, find closest match among millions of data points I have over there, and just suggest the nearest price. However, doing all this would take a lot of resources. We need high processing power. We would need a large amount of data stored such that we can access it really quickly. But with neural networks, we don't have to do that. Once we are done training the network that we are building, we won't have to again and again access the data. We just give it the information that we want to provide as an input, and it will directly give us the output that we are looking for depending on what we made it for. Similarly, for classification purpose as well, the usual way of classifying something depending on the data we already have goes something like this. You take in the input. For example, we have the similar data from above in which we already have the price this time. We just want to know whether the person looking for the car will buy it. Now, while doing so, we can just look at similar models in the past and see how many people actually bought it, and then compare the statistics to know whether the user will buy it or not. But in such cases, if for example, around I have 20, 25, 22, these are the mileages that I have. But if a car pops up with something like 17 as its mileage or 23 as its mileage, and some new values in these places, then what our algorithm would end up doing is find something closest. For example, I have 23, I'll go with this 22. And then whatever I had as the result over here, whether the person bought it or not, I can just provide it. But that would not be the most accurate one. So instead of doing that, we make our model be able to recognize what patterns the particular program is following or whatever the data is following. By recognizing these patterns, we are able to answer questions that are not already there in the database, and even be better than the usual algorithm where we end up comparing it with the previous data. So what exactly is happening over here? For example, let us consider a problem. I am trying to predict the price of a house. So what would it depend on? I have the variable size, and for example, the bigger the house, the more likely will someone pay for it, right? So I'll take size as a parameter over here, as an input over here. Then the next question that would come to my mind would be how many rooms it has, or how many people can live in it. So considering how many rooms, the number of rooms will also be taken as a parameter. And then what we would do is, let us see, I will also consider the locality, whether it is close to my workplace or not. So with that, I'll also consider the location, because I would also need to check if there are facilities available in the region. I don't want to end up buying a house outside the city and travel 5 hours every day. So I'll consider all these things. But when I'm trying to predict the price of it, what I'm going to do is take all this data, all the inputs I have, and feed it to a function. Let it be f of x for now. And this function would in turn give me the price. Now, how will it do this? That is something, and what exactly is the function f is something that we'll see in the later parts of the session. But this is what our neural network would usually do. For it, we will be providing it with the data as an input, and it will provide us with output, a single output that we desire from it. Now that, okay, so now that we have seen what a neural network is, let's move on to logistic regression. Now, I'm sure most of you have already studied the topic and you know what a binary classification is and how logistic regression does that. So this is just an algorithm that you use to output labels that are either 0 or 1, or whether to classify whatever you want to classify into two sections. So basically binary classification. So let's quickly take a recap over here. Now, I hope you remember this equation we have here. The variables in this are our usual x for input data, w for the weights that we have assigned for the data, then we have our bias b, and then we have the sigma, which is our sigmoid function. Now, here we are, this is what a sigmoid function looks like, by the way. And when we are, what we are trying to calculate over here, this y hat is the probability of a particular event happening. For example, I want to check whether a particular event will happen given the input data x that I am providing to it, and I want to know whether it will happen or not. So in this case, this would be how our logistic regression equation will look like. And for those who do not recall, the reason why we use a sigmoid function over here is that our data over here, the w transpose x plus b, is something that will give us a result anywhere in between a very large negative value to a very high positive value. However, we do not want that. We do not want a probability that lies outside 0 and 1 seems unrealistic. And that is not something that we will like to get as an answer. So we utilize this sigmoid function that we call as an activation function, which helps bring those values in our range to predict its probability. For here, sigmoid function would intersect the y-axis at 0.5, giving us the middle point of 1 and 0. Below it, we would consider that the event has not happened, or rather it will not happen, and above it, we'll consider that it will happen. So yes, this helps us categorize the output that we are getting into two classes. So let us consider an example. So what I have in front of me right now is an image of the digit 1, and I want my algorithm to tell me whether it is a 1 or not. Now for us, we know that it is a 1 as soon as we look at it, but now we want our algorithm to do that for us. So how do we do that? Let's take the image as an input data. We will consider that to be a vector, and then let w be the weights for each element inside the vector, that x vector that we are taking in as a data. Now for suitable weights, the result of this equation over here would be something like this. Okay, so I think I messed up a bit. So when y hat is greater than 0.5, we see that the probability of the image being 1 is greater than 0.5. So we consider it to be 1. And we say that it is a 1. Or rather, the algorithm will consider that to be a 1. And if that same is less than 0.5, pardon the mistake over here, is less than 0.5, then we classify it as it is not a 1. Now, how we get these weights and how we work with this is something that we will see. But if we closely look at it, this working is similar to what we call a perceptron, which is generally an algorithm for supervised learning of binary classifiers. Now, this may sound heavy, but until the end of the session, this will all be very easy for you. So a perceptron is basically used for binary classification. That's all we need to know. And logistic regression is something that does just that. So let's see. This algorithm enables neurons to learn and process elements in the training set one at a time.